we are at the last leg, 3 more talks to go. And this talk, we are going to focus on hyperparameter optimization and a software package called DeepHyper. I'm Prasanna Balaprakash. I'm a computer scientist at Argonne, and I'm going to do this session along with Misha, who will do the second part of this tutorial. Okay, so supervised learning or supervised deep learning. So if you take this problem, if you see, what is an ideal case? An ideal case, you take the model, you build the model, and then see if it performs well on the training data. If it is not, you go and increase the model complexity by increasing the number of layers or finding the right network and so on and so forth. Then if it performs well on the training data, which means that you have somehow learned the data or you have a good learning capability from the model, you go and try to test that model on the testing data. If it performs well, then you are done, right? If it is not, then you need more data, or you have to do some other sort of tricks to improve the generalization and so on and so forth. So you collect more data and do this in an iterative fashion. So this is sort of the ideal workflow. But we don't live in an ideal world, right? Often trying to get the model working for a particular data set is a challenging task. In particular, if the data is something that is not traditional, if it's not like classifying cats and dog images, if you're looking at more scientific data, then this problem is much more acute. So for beginners, making this work in an appropriate way is sort of a magic, but for more experienced people, it has become more like an art. In fact, more than 60 to 70% of the time, identifying or tinkering with the model to make it work for the particular data, it consumes a lot of time, more than 60 to 70% of the time. Okay. So one particular problem that we are looking at is, can we automate this? So there are several aspects of model building. If you have heard from the morning that several models are sort of sensitive to the hyperparameters that it adopt, and finding the right hyperparameters is a challenging problem. So what we are looking at is, can we automatically do this? So we can formulate this problem as an automated machine learning problem, and in particular for deep learning, what it transforms is, so you have the lower level problem. So the lower level problem is all about training. So given the data, given the model, we apply stochastic gradient descent, we identify the correct loss function together with that, and then apply it to minimize this error. So this is the training error. So that's the lower level problem, right? But the upper level problem is one in which you identify the right architecture, or for a given architecture and for a given set of hyperparameter, you go and solve a particular lower level problem. But then if you sort of think about, there are many different architectures, and for each architecture there are different hyperparameters that I can try, then this problem becomes a lot more computationally expensive, right? So for each combination, right? So for pick an architecture space, and then within that architecture space you have a handful of hyperparameters, and pick a hyperparameter configuration. You have to go and train them, and then you will get an error, and then now you have to solve a much bigger problem. That is the upper level problem. Okay, so what we are trying to do is, can we make this problem? Can we solve this upper level problem in a much more automated way rather than trial and error? Okay, so we are developing this software package called DeepHyper. It's primarily looking at how we can do or how we can solve the upper level problem in a much more automated way. It consists of 3 components. So the first one is hyperparameter search, which given a particular architecture, it has several hyperparameters, and you want to identify the right hyperparameter configurations for that particular architecture. So that component is hyperparameter search. And we also working on neural architecture search, which is a lot more experimental. But here, as you've seen in the previous talk, reinforcement learning. So we used reinforcement learning to automatically construct different types of neural architectures. Okay, so we use an agent. That agent will go and build different types of architectures, and it gets reward. So the reward is the accuracy, and using that reward, the agent slowly starts to build better architectures. So that's the neural architecture search component. And finally, to do these two things, to solve this upper level problem, we need to scale this, right? So because each evaluation is computationally expensive, and we cannot do this in a sequential fashion, in a one-by-one fashion. So we need to scale this on big supercomputers so that we can make this process a lot faster. And the third component is the workflow component, which manages distributing all these jobs on different nodes and collecting the accuracy values, giving back to these search algorithms. So for that, we use Balsam. So the rest of the talk, I'm going to focus primarily the hyperparameter search. So given a particular architecture, how to find the right set of hyperparameter configuration values. So the hyperparameter here means number of units, number of layers, batch size, the mini batch size, different types of learning rate, different optimizers, and so on and so forth. So there are many different hyperparameters for a given model, and we want to find the right set of hyperparameter values for this given architecture. So the algorithm that we use for this purpose is asynchronous model-based search. So at a very high level, the idea is there is another learning model which sits on top of this, right? So this learning model has nothing to do with neural nets, okay? So forget about deep learning, forget about deep neural nets. So think about some model that sits on at the top. It generates some hyperparameter configurations, evaluate them, take their accuracy values. So for each hyperparameter configuration, you plug them in the model, get the accuracy value, and give it back to the learning model. And then you do this iteratively. So the learning model, which is sitting on the top, tries to learn the relationship between hyperparameter configurations and their corresponding accuracy values. So once the model starts learning this relationship, then it can generate better configurations iteratively, and then eventually good or high-performing hyperparameter configuration values for this given model. So the initialization phase, you just have random sample, you do a random sample, get different type of different hyperparameter configuration values, and then the iterative phase, you do what is shown on the figure. So what is under the algorithm is Bayesian optimization. So you have seen the tutorial on Bayesian optimization or Bayesian neural networks. So the idea is similar. So let's say you have a 1D function, for illustration, consider this 1D function, and you have training points, and the training points are shown in black. In our case, these are hyperparameter configuration values that you already evaluated, right? So the Bayesian optimization here, what it will do is it fits different types of functions passing through these values that you already sampled, right? So if you have already sampled, then your uncertainty will be 0 at those points, right? So 0, 0, 0, because different functions passing through that particular point, your uncertainty will be 0. And if you don't have any points that is from the space where you which is far away from the points that are evaluated, then your uncertainty will be larger. Okay, so that's what the key principle behind Bayesian optimization. So what you will do then is using this information, you will go and sample in the regions where your uncertainty will be higher, or your model says that there is a room for improvement. So here, if you're just looking at this from an uncertainty perspective, just by sampling a point here or here, we can reduce the uncertainty to a large extent, right? So reducing the uncertainty means we are getting better information about the underlying function that we want to model, in our case hyperparameters to the accuracy values, and that can potentially lead to better sampling or better hyperparameter configurations. So that's the high level idea. So the typical way to do this is Gaussian process regression, but the challenge here is in the hyperparameter tuning, we have mixed integer space, which means that we have integer parameters, we have categorical parameters along with real parameters. Okay, so we cannot directly use Gaussian process regression, but we can use other types of learning methods to learn this relationship. In particular, we use methods based on random forest. Okay, so how this actually works? So I talked about sampling a point where there is high uncertainty, right? So you don't want to do that always, right? So given the whole space, you can have high uncertainty in regions where your performance are poor, right? Why we need to go and sample there? There is that's a waste of sampling effort, right? So it uses something called lower confidence bound, and the formula is simple. So you have a mu of x, which is the mean from the model, predicted mean, and sigma f of x, which is a standard deviation from the model. So your model predicts mean and standard deviation. So that is coming from the Bayesian idea, right? And you use these two information along with the parameter called beta to balance the exploration and exploitation. So the exploration is when you have large uncertainty, go and sample that region, sample a point from that region. Exploitation means you have a point, or your prediction says that there is a high chance that you are going to see an improvement there. You would go and sample that point over sampling from a point which has high uncertainty. Okay, so the whole idea is to balance this exploration versus exploitation. You need to do both exploration and exploitation, but you go and do exploration based on that beta value. So if you set the beta value to 0, what will happen? The model will always go and sample a point which the model says it's better. Okay, better than given a set of points, it will always choose a point that has a minimal prediction value, right? Let's say our objective is to minimize something. When you start increasing the beta value, then there is some sort of the trade-off. And then if you set beta to infinity, to set to a large value, what will happen? It will go and always select a point from region that have high uncertainty. It will just ignore the mean or whatever the good regions of the model. Okay. So here is a little animation that shows how you go and sample the point. So here is a one-dimensional illustration. So here is the output, and these blue things are the uncertainty, and the mean is given by the blue dotted line, and the green is the real function, which the unknown function, which we don't know, and we are trying to minimize. This function, which is we want to reach somewhere here. Okay. So we sample a point, those are shown there, and based on that there is this uncertainty. From those uncertainty we can use this LCB, lower confidence bound, to come up with something like this. So the lower confidence bound score is shown there, and then you will go and choose a point which has minimal lower confidence bound. So that is shown in the red. So after sampling that point, the next sample point, so again you give that point to the model and retrain the model. Okay. Once you retrain the model, now you see how the lower confidence bound measure changes over the input space. And based on that, we will select another point which is shown there. So that's marked as X, right? And you take that point, evaluate it, and then put back in the model, retrain. And then based on that, you will have another LCP score, and you keep on sampling from that. And then what you will see is finally, you have sample points here, and there is the model says, okay, there is no more improvement here, but I have now a high uncertainty over here. Let me go and sample that to see if I can minimize this model. So that's why your next point is at the edge of that, and so on and so forth. So so this is one point at a time. So in this case, what you are doing is you take a point from the model, or LCB selects a point, you go and evaluate that point and give back to the model, you retrain the model, and so on and so forth. So it's always one at a time, right? But that methodology, although classical, has limitations, right? If you are doing hyperparameter tuning, especially for deep neural net, if you sample only one point and you train for, let's say, 15 minutes, and you have to wait 15 minutes until you get the next point. So the idea is then how we can scale this method so that at any point of time we can evaluate several different hyperparameter configurations in parallel, and get the accuracy values, retrain the model, and sample more points, and do this in a parallel way. Okay. So that's where we do this multi-point asynchronous sampling, where the idea is, if we just, in a brute force way, if we sample those points, what will happen? So what you see here is, different sort of uncertainty estimate. Okay, so this is, a lot more uncertainty followed by this one and followed by this one. If you try to just blindly sample points based on the uncertainty estimate or the LCB, what will happen is, let's say we have to sample this many points, because our uncertainty is lot here, we'll get a lot more points from there. Right? If we don't know the evaluations, then we cannot retrain that, right? So if we want to sample 100 points at a stretch, we will be sampling all the points from this particular region, and that's something that we want to avoid. The reason being that as soon as you sample a point, you know that when you evaluate something here, you know a lot about that region. So you don't want to sample more points from that particular region. So that's why you have to do some conditional sampling, which is basically you sample a point here, and then using the predicted value, you retrain the model. You make this approach called constant liar that says, okay, as soon as I sample a point, I use the predicted value and then retrain the model with the predicted value. So this makes the uncertainty value to 0 in this region. So automatically, the method will go and sample some points from this region. And then you do the same, then it will move to the different region. You do the same, now it will again come back to that region, right? So this will allow you to sort of, explore different regions in the space with the different levels of uncertainty. Otherwise, you will be sampling from one particular region with high uncertainty, and that's a waste of sampling points. So that's what we do, and so this is you take the mean and then you retrain the model. So you take the LCB values to pick a point and then use the mean of that point and say that the actual value is that predicted value, and then go and choose the next point. Okay. So some comparisons. So we did a comparison of that asynchronous model-based search method with genetic algorithm, random search, and hyperband. So these are all different types of methods. And what you see here, so these are on different benchmarks. So each one of this is a different benchmark. This is MNIST example with multi-layer perceptron. It's a fully connected network. This is with a convolution neural network. That is CIFAR-10 with convolution neural network. GCN stands for graph convolution network, and RNN recurrent neural network, 2 different variants. So on the y-axis, what you see is the number of evaluations. So how many evaluations this particular method did within 2 hours of time. So the platform that we used is on Theta at ALCF and 128 KNL nodes, which means that there's one node that is doing the search, and there's one node for the workflow, and the remaining 126 nodes are available for doing evaluation, which means we can do 128 model evaluations at the same time. Okay. So what you see here, the asynchronous model-based search, because of the asynchronicity, can perform a lot more evaluations than the other methods such as GA, random search, and hyperband. The reason why genetic algorithm is not performing as many evaluations as asynchronous methods is because the GA is batch synchronous. So it takes a bunch of configurations, go and evaluate them, but it cannot go to the second iteration before all these 126 evaluations finish. Okay, so some of them can take a lot more time, and because of that, it cannot go and update the model or go to the second iteration. Why random search is not doing many? Random search is an asynchronous one, right? So you can just put 126, as soon as one finishes, you can generate a random configuration and put them back. The reason why random search is not doing many evaluations is because it was randomly sampling the number of epochs, and as a consequence, there are a lot of configurations for these benchmarks which were running for a lot of epochs. which is not necessary for these benchmarks because even with few epochs, less than 10 epochs, you can get high accuracy. But random search doesn't have any mechanism to learn that. Whereas the asynchronous model-based search, by evaluating few configurations, it learns that, okay, you know, if I do a lot of epochs, I'm not getting the accuracy in short period of time, so I'm not going to do that. I'm not going to sample that. So that's the reason why AMBS performs better than random search. And hyperband is another method, again, batch synchronous method, it falls short. How this corresponds to accuracy is what's shown here. So because we can perform that many evaluations, AMBS can find a lot more configurations with high accuracy. So what you see on the y-axis is out of this total configurations it evaluated, how many of them achieved more than 80% accuracy. So AMBS performs like out of the total number of configurations it evaluated, more than 60% achieved more than 80% accuracy. Similarly for the MNIST CNN, CIFAR-10 there is only few because each evaluation is a lot more expensive there, but we can see similar trend over all these different benchmarks. So this is the scaling efficiency. So of course you can see now random search has much better scaling efficiency because you know you always run those configurations, and as soon as one of them finishes, you randomly sample another one and put them, and irrespective of the number of epochs, it keeps on occupying all the node configuration, all the nodes, right? But this doesn't translate it into accuracy. That's what we have seen in the previous slides. So whereas AMBS and GA sort of have 50 to 60% node efficiency, worker utilization, so this is sort of an old result. We improved the worker utilization to a significant fraction with our recent updates to the package. Okay, so this is on Cooley with the GPU. Again, similar results with respect to total evaluations. With that, I hand over the presentation to Misha, who will cover some internal aspects of DeepHyper and the algorithms.
Hey everybody, so I'm Misha. I have been working with Prasanna on DeepHyper, and I'm the primary developer of the Balsam workflow system that it uses as an execution backend to run on some of our machines at ALCF. So I was going to go basically continuing straight from where Prasanna left off and give a real hands-on example of a Bayesian optimization in the simplest possible case. So if you guys want to open up a Colab notebook from this GitHub URL, this is pretty much the simplest possible real case of using sequential Bayesian optimization to tune a real deep neural network. So I've stripped away all of the complexity here of there's no DeepHyper, there's no parallelism. This is just one sequential thing that runs on one core. But I think it illustrates the main idea of what you're doing in a real Python workflow. And then from there, once you understand this process, I think it's very simple to pick up DeepHyper and start running on hundreds or thousands of nodes. So as Prasanna mentioned in the beginning, your hyperparameters can be concerned with model architecture or other tuning parameters in the process of, for instance, optimizing the parameters for a given model. So here, this is pulled out of that example notebook. I'm just going to kind of highlight parts of the notebook on my slide. You have a function in Python you call run model, and this encapsulates the whole process where you build the neural network you're interested in, you feed it the data, train it, and you return the objective, the thing that you're trying to optimize. In this case, the problem is cast as a minimization, so what we're going to look for is the minimizing the loss or maximizing test accuracy. So here are some examples, like what are hyperparameters? They're all shown in this as a basically keyword argument to this function. So I just selected a few examples for training an MLP or multilayer perceptron with 2 hidden layers on the MNIST classification task. So these are a couple of highlighted architectural parameters like number of units or the dropout. And then you have other hyperparameters like learning rate or batch size that control the training process and how your model is updated. Now, how do you choose these hyperparameters? So as Prasanna kind of motivated in the beginning, you can kind of treat them as good rules of thumb. You can read lots of blogs and get, kind of find the right settings based on your gut feeling. Or you can treat this like a proper optimization problem and run this outer loop searching over hyperparameter space and doing this inner search over model parameters for every set of hyperparameters. This notebook uses one particular nice Python framework for doing this kind of Bayesian outer loop optimization. It's called Scikit-Optimize. And so I'm just going to show a little bit of what this notebook is doing with Scikit-Optimize. The first step when you want to do a tuning is to define your search space. So this is really clear here. In this example, I want to keep it really small. So I have a tiny, actually too small model with very few hidden units, and we're only going to train it for one epoch. And I'm like, okay, I want this to go fast. So how can I get decent performance given those tight constraints? So I'm going to consider changing the batch size between 64 and 512 training examples per mini batch. And I'm going to vary the learning rate continuously between 10 to the minus 3 and 1. And so that's shown here as these two tuples in this list, which is the problem definition. And Scikit-Optimize was actually intelligent about how it treats different types of parameters. So because these are two integers in Python, it's going to treat that as a discrete integer space and give you just those 4 values I showed. And then this is going to be a continuous range. And then I just have a quick mapping here that takes a list with the 2 items and gives you back a mapping to the keyword arguments that you want to pass into your model run function. So that's pretty much all the setup you need. And then the optimizer here, we create an instance of this Scikit-Optimize optimizer class. We give it the problem dimensions that I just showed you. So this is our batch size and learning rate, the kind of surrogate model we want to use. So this is extra trees, which is related to the random forests. It's another ensemble of decision trees. And that's our outer model. Don't confuse that with the model you build. This is some canned regressor that's going to try to predict the accuracy of the models just given the hyperparameters. And so this is some parameters on how we evaluate the acquisition function. And this parameter says, let's visit 6 points randomly. And then we feed all of those to our extra trees model. And then we start drawing points from the model. So when you do that, it's super easy to use. You actually can control the optimization loop. And this is the same kind of code that DeepHyper is using for AMBS. We add some parallel logic, and we use Balsam to parallelize things. But in the notebook, you can just write a nice little sequential loop here. So we call optimizer.ask to ask for the next value. And then this value, we turn it into the mapping of keyword arguments to our function. So this is where we pass it into our Keras model or TensorFlow model, whatever you want to use. You can see it's all very model agnostic. And then we run that model, and we get back our objective, and we give it back to the optimizer here in this call to tell. And so this is a sort of completely contained black box optimization loop. You can see here that it has nothing to do really with neural networks. You can optimize any kind of function where you don't have information on gradients. And so here is just a result from one run of this that I got out of that notebook. So on the y-axis, we have the test accuracy of a given MLP on the MNIST data set. And then the x-axis is just the iteration count. So the first 6 points we got, because I put 6 there, are drawn at random. And you can see how the test accuracy is kind of all over the place. And then starting on the 8th and subsequent, we get accuracy consistently over 80%. And so yeah, that kind of illustrates what you get out of Bayesian optimization. So this is a tiny model, and we only have 2 hyperparameters. So you can get lucky with random search. Maybe you don't need to do this, but when you start dealing with a large number of hyperparameters and you have a serious model that you want to run for, maybe it takes several hours to train, it could be useful to take this process and parallelize it to find effective hyperparameters. instead of relying on that black magic. So again, DeepHyper is one way to parallelize this on systems at ALCF, or you can run DeepHyper on your own laptop as well. It's on PyPy, so it's something you can just pip install if you want to look at it in your own time. We have documentation up on readthedocs. But the important thing, if you want to try this out on Theta, when you start searching over models, is that we have already production-ready models there. So you can just do module load DeepHyper, and you get a Python environment with everything you need to start working. So I would invite you to check out the tutorials here. We have one of Prasanna's colleagues, Romain, put together really nice detailed tutorials that sort of walk you through how to take that notebook and run it inside of DeepHyper. And then there's instructions for running on Theta, Cooley, and ways to adapt this to other domains. And then there's also a neural architecture search there, which is a whole nother ballgame that we're not even getting into. So that's about it. I'm not going to go into any specifics because if you want to do it, just go there. But what I will talk about, because this is maybe worth mentioning, is that DeepHyper on these systems is using Balsam as a workflow manager to actually run these jobs. So your search is generating hyperparameters, and maybe you have 1,000 nodes and you want to run 1,000 different neural networks at the same time. Balsam is what's taking care of this, but it's actually a general purpose way of running Ensemble jobs on Theta. So with that, let me kind of look at a scenario that you're probably familiar with. Let's say you have 5 compute nodes in a debug job on Theta, and then you want to run some scripts on it. So one way that you can take an application and run several instances of it is to just write your own bash script. So say you have something called my app, which takes some input arguments and runs. You can invoke this with a standard MPI launcher on your system, like AppRun in the case of Theta and other Cray platforms. And by backgrounding jobs, you could basically create several of these. In this case, we have 3 jobs. One is running on 2 nodes, or one is running on a single node. The other 2 are on 2 nodes. And then after we issue all of these, we just wait on them to run. And if you look at ALCF pages, they'll say, this is an effective way to run many jobs packed into one job script. But that can be effective, but it becomes challenging when we go to larger numbers of jobs. So what do we mean by workflow? It's just a way of running the jobs that you need to run. And sometimes those bash scripts are perfectly fine. So you could just manually submit jobs to the scheduler. You can have on Theta up to 20 jobs in the queue. And if you stay organized with your directory structure and you're decently comfortable with bash and other shell tools, this is perfectly fine. But when we start getting into larger numbers of runs, there's a lot of challenges there. So that script I just showed you launches everything and then sleeps. So what if you want to run jobs one after the other? How are you going to do that? What if only like 50% of the jobs finished? How are you going to track which tasks are finished, which ones are left to run again? How are you going to handle timeouts if there's partial progress? This becomes really unmanageable when you go to thousands or millions of runs. And this is where something like a workflow comes in. So you can either fight these limitations by building your own scripts, or you can pick up things that we kind of produced for you, like Balsam. So the big idea with Balsam is you just tell it about your jobs. There's a database that belongs to you. It runs as a Django application, so it's actually something that it's pretty easy to tie into a web interface as well. You dump your jobs into Balsam and you let it do the rest. So it will submit jobs to the scheduler and make sure that things run in parallel one after another, and it will take care of restarting jobs that failed and so on. It doesn't require modifying your code at all. You just throw in commands that you already have, and there's fairly strong fault tolerance. So if some instances of your run are killed, for instance, under DeepHyper, you may have some hyperparameters that lead to running out of memory. And Balsam is resilient to these kinds of issues, and actually a lot of the results that Prasanna showed are using this to stay alive in spite of bad hyperparameter configurations. And then at the end of runs, because all the metadata goes back into a database, you get all kinds of statistics on your runs available at a glance. Yeah.
So you did mention that for ALCF systems. So is there anything particular causing you to run on a Slurm or any other type of system?
Right now, that's on us, and it's on me. So there's a plugin. So you can. It actually used to interface to a lot of schedulers, and it's a modular plugin. So basically, the MPI launch interface, the scheduler interface are swappable, and since then, the support for Slurm has atrophied, but I think that's under a day's work, and I need to do that soon. So I'll do that. Right now, it's well supported and in heavy production on the LCF though. So here's an example of the kind of stuff you get for free when you run in Balsam. In this case, there was a computational chemist that wanted to run a few million DFT calculations. So they throw them all into the database at once, and then they ran over the course of 3 days here. So you could see on time axis, and then you can see the black curve gives you the number of completed jobs over time, and the blue curve is how many jobs are running at any given time. And so you can see here, this is in increments of 802 nodes. So there were 2 jobs running here, totaling 1,600 nodes, and then down to 1, and then all the way up to 5 at one point. So something that's convenient here is that you can run many Cobalt jobs simultaneously, and they're all pulling tasks out of the same service. So you no longer have to think about which jobs run in which batch jobs. It kind of is handled on your behalf. Again, this is another thing that's in production. So you can module load Balsam if you're running on Theta. Otherwise, it's something that's fairly straightforward to install into your own Python environment. And yeah, I would invite you to check out Balsam documentation for general purpose needs, or if you just want to run DeepHyper on top of Balsam, go check out the tutorials there. And yeah, that's all I've got. Yeah.
I have a question or comment about the multi-point asynchronous sampling. Could you just do a sample like a PDF of your lower confidence bound, and then you wouldn't have to evaluate the Gaussian process each turn, right?
So we are not doing any. So we are not using GP. So if you think about to handle the mixed integer space, right? Mm-hmm. So because we have integer parameters, categorical parameters, and real parameters, we cannot use GP directly. Because of that, we don't have a closed form for that, and we cannot sample from there. So that's why we have to rely on sampling rather than using closed form to identify these problems.
Okay, yeah, that makes sense. Thanks.
Yeah.
Can you apply something similar to DeepHyper, but to optimize the network topology and structure, let's say?
So that's the other component, which is also experimental now. So that's why we didn't cover. So that's the neural architecture search, which is basically trying to experiment with different types of architectures. So we use reinforcement learning for that. And the idea there is we use agents, like multiple agents, all running in parallel. And each of the agents samples a number of different architectures.
But I'm saying, let's say for a given neural network type, let's say fully connected.
Yeah.
I want to find the optimum number of hidden layers and number of neurons per layer, basically.
You can cast that as a hyperparameter optimization problem too. So there are, there's a lot of examples in the literature where they use this kind of stuff with nested hyperparameters. So you can have one hyperparameter, which is the number of hidden layers, and then conditional on that, you can control the number of hidden units in each layer and so on. So this is well explored.
So the MNIST MLP example we had as one of the benchmarks is basically doing that. So the number of units and number of hidden layers and number of units per hidden layer, both of them becomes hyperparameters. So for the MLP we can play with that. But once you start doing the CNN, trying to optimize the filter sizes and so on and so forth, then you can in some sense cast that as a hyperparameter search because your network is stale. is stable, right? So,
Yeah.
but the case for the neural architecture search is, you want to come up with a completely different architectures. Like you want to explore that space, and try in particular trying to come up with different types of skip connections. So you have seen that the skip connections make the neural network a lot more easier for training and for generalization and so on and so forth. So the addition, where to connect those skip connections, I'm taking an input layer, can I connect to the second layer, third layer, or fifth layer? So those kind of things we can cast that as an architecture search problem.